my recording. Mario only, not Alana Banana. In case she's thinking that. Hey, alright, so before I tell you the direct test, I want to tell you motivation behind the direct comparison. So basically what we're going to be doing is comparing series that look very similar to like a p-series or a geometric series, but maybe it's slightly off. We're going to be comparing it to a series we know how to and then basically forcing the other similars to converge or diverge. Let me get over here by the mic. Sometimes we may encounter a series that looks slightly like a normal series. Like, for example, we know 1 over 2 to the power of n is a geometric series. But if you change it ever so slightly, like maybe replace the 1 with an n instead. So if you change it ever so slightly like this, now this is not a geometric series. And we've seen this before, and we've done like, well, nth term test doesn't work. I think we did ratio test with something like this. Another example of a very nice familiar series that we easily know how to do is 1 over n cubed. This is a p-series. But maybe you change the denominator to n cubed plus 8. Now this is not a p-series. Okay, so I'm going to teach you today how to deal with series that look very similar, but like slightly off from a geometric and a p-series, and compare it to a function. Okay, so here's the main idea, and I'll tell you the criteria for the test. So the main idea is you're going to compare difficult-looking series. Okay, write this with me. Compare difficult, or can you write this with me, please? Looking series with the familiar and simpler looking series. So with a familiar and simpler looking series, and use direct comparison test. Okay, so I need to tell you what direct comparison test is. This is just when to use it. When a series looks very close or similar to something nice and easy that you know how to do. Also, you can use this when the nth term test doesn't work. So can use when the nth term test doesn't work. It's not a factorial. That's an exclamation point. Okay, here we go, direct comparison test. So again, the idea is we have two series here. All right, let me read it. So let 0 be less than a sub n is less than equal to b sub n. So these are two series, a and b. All this is same than the other. Okay, so this means b sub n is the bigger series. A sub n is the smaller. Okay, so the criteria for converges is if the infinite series b sub n converges, then a sub n converges as well. Second criteria, if infinite series of a sub n diverges, then b sub n diverges as well. Does that make sense to you? Okay, great. I'm going to summarize these two, 1 and 2, in terms of the airplane analogy here that I gave you, so that way it makes a little more sense. I want to use blue. 1, 2. Okay, B is the bigger series, the bigger airplane. A is the smaller series. So what it's saying on number 1 is, here I have my airplanes again. So if the big series converges, it's saying that A, the smaller series, is going to converge as well. So basically, if the higher airplane, here, let's write it. The higher airplane aka the bigger series, goes down, then the lower plane smaller series, also goes down. Also goes down. And then we said that going down means converges. Let the record show Byram just walked in. Late as heck. Alright, so that's what the first criteria say for convergence. Byram, can you not walk in late? Conversation? Thank you. Second criteria, now it says if A sub n diverges, then B sub n diverges as well. So that's what this means right here. So if the smaller series diverges, you see my plane's going again. If the small series diverges, it's forcing the bigger series to also diverge. Did you catch that, Leela? Saw the planes? Huh. Then this wouldn't work. Where'd my apple go? We'll get there. You're too advanced. You're too ahead to me. How do you do it? That's amazing. Okay, let's write it real quick. If the lower plane goes up, right, the lower plane's a smaller one. I'm not going to write it again. Then the higher plane is the bigger one, goes up as well. Also goes up. And we established that going up means diverges. Okay, enough of this airplane talk. No, we're going to keep talking about airplanes, actually. Let's do examples. Okay, ready? Examples, use a direct comparison test. Obviously, you will never see directions that tell you to use a direct comparison test. You just know when to use it when it looks very similar to something you already know. So number 1, first of all, this looks like a geometric series. If we didn't have this 2 here, this would be a geometric series. You would do the geometric series test. But we have that 2 plus 3 to the n. So we're going to compare this guy to a geometric series. Why? Because geo's easy. We know at the top of our heads, wait, before I even discuss if this converges or diverges, the first thing you need to do is determine which one's bigger and which one's smaller. So 2 plus 3n is a bigger denominator. The bigger the denominator, like the smaller the fraction overall. So that makes this guy, our original series, be the smaller one, less than or equal to. Okay, you have to see which one's bigger and smaller first. And then you're going to do your test on the new series you're comparing this to. So this is a geometric series with r equal to 1/3 less than 1. Okay, we know this geometric series converges. Now, to see if our original series also converges, you need to check the airplanes. So you think, or even just use your little airplanes in your hand sometimes. If the bigger series, right, this guy's bigger, converges, is that going to force the other series, the smaller one, to go down? Yeah, that checks out. Okay, so the direct comparison test works here. So we can state the direct comparison test test that 1 over 2 plus 3 to the power of n will also converge. Great, that's it. Yes. Okay, I'll write it over here on the next example. Because 2 plus 3n is a bigger number than 3n. So the bigger the denominator, the smaller the fraction. For example, like 1/4 and 1/2. This is a smaller, sorry, that's a bigger denominator, so that makes that one smaller one. We'll write that on the next example here. Okay, number 2. 2 over n minus 3. Okay, so by the way, like, you know, like when to use this? Well, no, what's that one? Nth term test for divergence, does it work? You could do integral test on this, but we don't want to, right? Avoid that at all costs. This is a good one that you want to do the direct comparison test on because it looks very similar to a p-series. 2 over n. Okay, first we need to see which one's bigger, which one's smaller. N minus 3 is a smaller denominator than just n. So the smaller the denominator, that it's going to be a bigger series like this. Let's write that. It can get confusing. The smaller the denominator, the bigger the number. Are you writing your notes? Uh-oh. The bigger the number. Yeah. This is a smaller denominator. So this series is bigger. That's why it's greater than. Yeah. No. We talked about this last class. Sorry, it doesn't make sense to you, Fedor. But, you can't just get the behavior of a function by just plugging in n equals 1. It's as n approaches infinity, so like later on as you plug in bigger numbers, you will see that this is going to be the bigger one later on as n approaches infinity. I don't know. It makes sense to me, Fedor. Sorry. I'll try to clarify more later. So right here, now we're gonna do the test on this p series. P is equal to 1. The series diverges. To see if our original series will also diverge, like compare. So we have the bigger series, no, the smaller one is diverging, going up. It's going to force the bigger one to also go up. So this works. You have to check this every time. It doesn't always work, like Timmy was already getting at, because he's so smart. Okay, this one also diverges. I'm going to do one more with you. Number 3. Doesn't, like right away, like it doesn't scream like it's super similar to any series. The limit 0 can't do nth term test. You actually can't do integral test. You cannot do, because you can't do u sub unless this was like a n squared. Remember, you do integral test if it looks u subby. So you do have to do the direct comparison test. If you're not sure what to compare it to, you kind of want to think like how you do with limits. Like look at the degree in the numerator. Like look at the term in the numerator with the biggest degree and the one in the denominator with the biggest degree. Again, like limits. Look at those only and then simplify from there. And then that will be what you end up comparing it to. So if you simplify, this will be 5 over n squared. Okay, so that's what we're going to be comparing to. Which one's bigger? N cubed is bigger than n squared, so therefore our original series will be the smaller one. Now let's do the P series test. P equals 2 converges. Okay, if the bigger series converges, will that make the little one also? Force the little one to also converge. Are you visualizing the airplanes in your mind? It works. That does work. Okay, so this guy also converges. Great. If you have questions, ask me now. If you're good, go ahead, try out number 4 now. Guys, only like 4 guys, like maybe more. Notice that direct comparison test didn't work. Number 5, sorry, just kidding. Number 4. Okay, you're comparing it to 1 over the square root of n. This guy is bigger. This is a P series. Since P is 1/2, this series diverges. Remember, think real life. When these real life airplanes right here, when they're flying, and the smaller one, wait. The smaller one diverges, this does not force the bigger one to move at all. It's not forcing it to diverge also. So you see, this is when this doesn't work. So that's why I'm saying you have to check it. Doesn't work. Let me tell you what to do here. So what you're gonna do is just choose a different series that's similar to 1 over square root n, and then try that, see if that works, okay? So here's what I'm gonna compare it to now instead. Instead of 1 over square root of n, let's look at 1 over n. Why? Because I said so. No, they're very similar. This is fine to do. I'll show you on the graph after this example why it's okay to compare 1 over square root of n to 1 over n. When you graph them, they're very similar. Like, they're pretty close on the graph. All right, so now comparing to 1 over n, let's see, n is now the bigger denominator, so this guy is now smaller. Oh, so we change the size here. This is a harmonic series. P is 1, this is going to diverge, so does it work now? Try it. If the smaller one diverges, look, it works now. Look, behold with your eyes. When the small one diverges, it works. It's forcing the big one to also diverge. Okay. Put diverges and compared to this series, I saw this on a test, this would be wrong. Yeah, you have the right answer, but you did it the wrong way. You need to compare it to the correct series, just like I did. Okay, so now we can say the series diverges. Alright, cool. So make sure you check it every single time. If it doesn't work, just compare it to 1 over n. That often works, honestly. I've never not been successful with that. Okay. Alright, get to work. Oh wait, let me grab this on Desmos, if you care. I had a girl in 3rd that was really upset about me comparing those two. I don't know, dude. She was like in a fedora mood or something. She was like, you can't just do that. I was like, yeah, you can. So I've graphed 1 over x and 1 over squared x, just in case you want this to make more sense to you. Like, these are, you know, the behavior of the function's very similar, so it's okay to compare it to 1 over n. It's not like I'm comparing it to like a log or something like crazy. Crazy different. Okay. Do your math. I'm gonna stop recording now.